Hello class, welcome to this video on 5.7 review. So let's go ahead and get started with the problems. So problem set number 1 is about using the multiplication counting principle. So it says here, online passwords help protect confidential information. One website allows users to choose a password that can consist of capital letters, lowercase letters, digits, or any of 4 special symbols. The only other requirement is that the first character must be a letter. How many different 5-character passwords are used? So in this case, they said we're looking for a 5-character password. So 1, 2, 3, 4, 5. And they said that this has to be a letter. This could be anything. So these could be any. All right. And so there are 26 letters, but then it says capital and lowercase. So it could be any of those. So there's actually 52 options, right? 26 plus 26 for letters. Now, so I'm going to choose one of those. And then any, for the second character, I can use any of these or digits or 4 special symbols. So that means I got 52 letters, 10 digits from 0 to 9. And then I got 4 special characters, so that's a total of 66 characters. Okay, so then we got 66 of anything. I have 66 options for that. Now, since I can repeat, it doesn't say anything about not being able to repeat. That means even if I chose one of these, I still got 66 options left, okay? And so remember, by the multiplication counting principle, we multiply all those ways. That gives us 986,686,272 possible 5-character combinations. All right, so number 2, determine how many different computer passwords are possible if digits and letters can be repeated, and then for part B, they cannot be repeated. We have 3 digits followed by 3 letters. Okay, so 1, 2, 3. These are digits. So digits, 1, 2, 3, 4, and so we got letters. All right, so we have 10 digits from 0 to 9. I could use any of those, and it says we can. It says for part A, they can be repeated. So let me do this. This is part A. They can be repeated, and then part B, they cannot be repeated. So for part B, we have 10 for both of these, but then once I use up one of these digits, I have 9 digits left, right? Not for part A, but for part B. For part A, you can repeat, so you still got 10 digits, still got 10 digits. This one you can't repeat for part B, so it's 10, 9, 8. Okay, so hopefully that made sense. And then, okay, so, and then for the letters, there's 26 letters, and then we can repeat, so it's 26 all the way through. But for this one, we cannot repeat, so 26, 25, 24, and then 23. Go ahead and figure out what those numbers are. So we got 10, basically 10 to the 3rd power. If you think about it like that, 10 to the 3rd power times 26 raised to the 4th power, because there's 4 of them. So we get that as our answer. Okay. All right, so now we're going to do 10 times 9 times 8 for part B. And we get 258,336,000. All right, and then it says 2 digits followed by 5 letters. And again, we're doing part A and part B. 1, 2, 3, 4, 5. Okay, so we got 2 digits and then 5 letters. Okay, so then again, 10 times 10, and then we got 26. And then for part B, it says cannot be repeated, so it's going to be 10, then 9. Okay, and that's it. And you can go ahead and get the answer for that, but that's how you would do your work. All right, so number 3, how many 4-digit odd numbers can be formed if no digit can be repeated? All right, so here we go. We got 1, 2, 3, 4 digits. Remember that the last digit tells you whether it's going to be odd or not, right? So we need this to be odd. And then it says these could be any, right? Any number. So here we got 1, 3, 5, and 7, and 9, right? Those are the numbers that we can use. 1, 3, 5, 7, and 9 in order for that to be an odd number. Well, that's 5 numbers. So we got 5 choices. Now, if I use one of those numbers, how many numbers do I have left? Well, I have 9 numbers left if I use up one of them, because before I had 10, right? So now I only have 9 numbers, and then 8, and then 7, since I cannot repeat. All right, so here we can multiply that. 9 times 8 times 7 times 5. So we have 2,520 possible combinations. All right, so now let's look at number 4. It says how many odd 2-digit positive integers greater than 20 are there? All right, so here we got 2-digit numbers, 2-digit integers, and it has to be greater than 20. And it has to be odd here, right? So, and then this has to be 2 or greater. So this digit has to be 2 or greater, because this is going to make it 20, 30, 40, 50, right? Anything bigger than 20. And this has to be odd numbers. So we got 5 options for that, for the odd number. And then we have 10 options, or no, not 10 options. It has to be 2 or greater. So that means 2, 3, 4, 5, 6, 7, 8, 9, right? So that's basically everything except for 0 and 1. Okay, so that's got to be 8 options then, right? If it's 2 or greater. So then that's 8 times 5. So that should be 40 possible 2-digit positive odd numbers greater than 20. All right, and then it says how many even 3-digit numbers? 1, 2, 3. So this has got to be even here. And then it says using the digits 1, 2, 4, 7, 8. Okay, so for even, we got 2, 4, and 8. So we only got 3 options for the even, right? Now, they don't say anything about being able to repeat or anything like that, so we can assume that we can repeat, right? So in this case, we know that, so we have 1, 2, 3, 4, 5 numbers. We got 5 numbers here, and then another 5 numbers there. So 5 options for the first one, 5 options for the second one, and only 3 for the last one because it has to be even. All right, we multiply those together, 5 times 5 times 3, and you get 75 possible even 3-digit numbers using those digits. All right, so I got problem set number 2. This was about calculating factorials. All right, so calculate the following: show work and use a calculator factorial function. So we got 15 factorial. 15 factorial is 15 times 14 times 13 ... all the way to 1. All right, so we just got to multiply that together, and that's it. All right, now 15 factorial is an incredibly big number, right? So when we do this, you do it on the calculator, you get a really big number. So let's write this out. All right, so look how big that number is. So we got 1,307,674,400,000 for 15 factorial. So an incredibly huge number. All right, calculate the following: show work and use a calculator function. Okay, so we got 10 factorial. Now, when we have 2 factorials like this, remember it's good to continue to multiply until you get to the bottom number factorial, so that way you can cancel it out. And so now we only have 10 times 9 times 8 times 7 times 6, which isn't as bad, right? So we can go ahead and do that. So we got 10 times 9 is 90. So then we got, so 10 times 9 times 8 times 7 times 6. So we got 30,240. All right, and then let's look at the next one. All right, so next problem is we got 9 factorial divided by 2 factorial times 5 factorial. So we got 9 times 8 times 7 times 6 times 5 factorial. And 2 factorial is just 2, because 2 times 1. And then we got 5 factorial, which cancels. And we know that 6 divided by 2 is 3. And so really we get 9 times 8 times 7 times 3. Okay, which is 1512. All right, and let's look at number 4. It says calculate the following, show work and use calcular function. Okay, so again, we got 8 factorial, 8 times 7 times 6 factorial. And then we got 3 times 2 factorial. And then we got 6 factorial, 2 factorial, these cancel. And leaving you with 8 times 7 times 3, which is, we got 8 times 7 is 56, or 7 times 3 is 21, and then 21 times 8, here's 168. All right. Okay, so let's look at the next problem set. The next problem set is about using the multiplication counting principle for team batting order and using factorials. So suppose you have 6 homework assignments to complete one night. In how many different orders can you complete all of the assignments? So here we're using order. So we just have 1, 2, 3, 4, 5, 6 assignments. So for the first assignment, we have 6 options, and then 5, and then 4, then 3, then 2, then 1. So in other words, we have 6 factorial options, okay? And 6 factorial, see what that is. It should be 720. Okay, so we have 720 different possible orders to do our homework. All right, number 2, Mario has 10 science fiction novels on a shelf in the bedroom. How many different ways are there for him to arrange the books on the shelf? So again, that's 10 times 9 times 8 all the way to 1, right? So it's 10 factorial, which is 10 times 9 times 8 all the way to 1. Okay, 10 factorial is a large number. Let's calculate it. So we get 3,628,800 possible arrangements of the books on the shelf. At the beginning of class, Sharice's teacher makes a special offer. She will dismiss the class early if they can make all possible arrangements with the 15 students in the class in a single file line. How many such arrangements are there? Should the class take the offer? Explain your answer. Well, considering how big 10 factorial is, 15 factorial is even is bigger. So I don't know if this is going to work out. So we got 15 students do all possible arrangements. That's 15 factorial. That's 15 times 14 times 13 all the way to 1. And that number right there is over 1 trillion. And remember, we calculated that earlier, or something like it. So 1,307,674,368,000. So should the class take the offer? Definitely not, right? They should not, as they will never have time to do it. All right, so number 4, Miss Clore has 28 desks in her classroom. She numbers the desks from 1 to 28. On the first day of class, she places identical slips of paper numbered 1 to 28 on a hat. Each of the 28 students in her statistics class draws a slip from the hat upon entering the classroom to determine his or her assigned seat. How many possible seating assignments are there? Well, there's 28 factorial seating assignments. which is it's such a big number. It's 3.05 times 10 to the 29th power. That's how many. Now, just to put this in context, how big this number is, there's only 28 students when we do this. This number is way bigger than the number of grains of sand on the Earth, which is around 7.5 sextillion grains of sand. If you look at it, it's like an enormous amount of grains of sand, but that doesn't even compare to this number. Okay, so it's an enormous number. All right, so let's look at problem set number 4. All right, so the next problem set is calculating permutations. So let's do this. Number 1. Okay, so it says we want to do the permutation of 10 objects taken 10 at a time. That's going to be 10 factorial divided by 10 minus 10 factorial. Well, 10 minus 10 factorial is 0 factorial, which is just 1. So it's just going to be 10 factorial. All right, and we know what 10 factorial is. So you can go ahead and put that answer here. I won't write it again here, but it was a number that was in the millions. And for number 2, we have 6, the permutation of 6 objects taken 2 at a time. I guess 6 factorial divided by 6 minus 2 factorial, which is 6 factorial divided by 4 factorial. So 6 times 5 times 4 factorial. That way these can cancel, and you get 6 times 5 is 30. All right, so number 3, we got 8 factorial divided by 5 factorial for the first one. For the second one, we got 5 factorial divided by 3 factorial, 5 minus 2. Okay, and notice that these factorials cancel out, so it works out very nicely. And then this 8 factorial, we can do 8 times 7 times 6 times 5 times 4 all the way to 3 factorial. That way the 3 factorials can cancel. So we just end up having 8 times 7 times 6 times 5 times 4. All right, and so we got 6,720. All right, and then let's look at the next one. So we got 7. Okay, so for this one, I would highly suggest doing a calculator to do this. So using the permutation function. A really good option for doing this online is Desmos. So if you go to Desmos Scientific Calculator, it can do permutations and combinations for you. Okay, so I just wanted to show you this on Desmos. So we go to Desmos, let me just zoom in. It's okay, a little bit too high. But we go to function, and then we go to NPR and NCR. So there's a combination, and there's even the factorial here. So NPR, and then you're going to type in 7, 3. So that's going to be the permutation of 7 objects taken 3 at a time. And then it was a fraction, and we want to multiply that by 3 permute 2. There you go. And then divide that by 10 permute 5. Okay, there you go. And there you go. So we get 0.042 for our answer. All right, so here you go. So you got 0.042 for our answer. And you could just use the answer, right? That there. You don't have to worry too much about it because there's so many permutations in there. It'll be a pain in the butt to write all the factorials. All right, so problem set number 5 is using permutations to solve problems. So Declan has 100 songs on his playlist. He is going for a run and has time to listen to 8 songs while he runs. Declan decides to use a random shuffle feature to determine which songs will play and in what order. And it says the random shuffle feature does not allow any song to be played twice. How many different lists of 8 songs are possible? So he's got 100 songs, and we have 8 songs, and then it's going to do it in that order. So we got 100 permutation of 100 songs taken 8 at a time. So you get 100 factorial divided by 92 factorial, which is 100 minus 8. So we have 100 times 99 times 98 all the way to 92 factorial, which, well, let me just write it out. 93 times 92 factorial, but then the 92 factorials cancel. So we have 100 times 99 times 98 all the way to 93. And again, using the permutation function on the calculator on Desmos or whatever calculator you have, is 7.5 times 10 to the 15th power lists of songs. All right, number 2, Mr. Velman has a test bank with 75 multiple choice questions on lesson 5.7. The test bank comes with a random number generator that will select and arrange questions to make different versions of a test. How many different versions of a 10-question multiple choice test could he make? Okay, so we got, since order matters, we're doing a permutation. So 75, choose 10. 75 factorial divided by 65 factorial. And you could just do the answer on the calculator because it's a big number. This is 3 times 10 to the 18th power. All right. A soccer team has 11 players on the field at the end of a scoreless game. According to league rules, the coach must select 5 of the players. So we got 11 players, 5 of the players, and designate an order in which they will take penalty kicks. All right, so it's 11 permute 5, so 11 factorial divided by 6 factorial. And so 11, so we could just write the answer using the calculator. So we got 55,440. Actually, this is not too bad. This is not as bad as I thought. It's just 11 times 10 times 9 times 8 times 7 to get that. So we can write that easily. All right, so number 4, letter lock padlocks open when a correct sequence of 3 letters is selected on the dial. So 3 letters, and then it says the dial has 20 letters on it, and letters cannot be repeated. How many different sequences of letters are possible? All right, so since they can't be repeated, I mean, you have 3 slots. We have 20 letters, then 19, then 18. But that's the same thing as 20 permute 3, right? So when you do that, you get 66,840. All right, guys, that's going to do it for the video. I hope you found this useful and informative. As usual, I'll see you in the next one.